Good morning. My name is John Baty, and I'm delighted to be a Science Research Fellow at Heritage Science for Conservation. We are funded by the Andrew W. Mellon Foundation to build a bridge between conservation scientists and conservators. And this is proof of our emotional proximity here, and this is proof of our physical proximity in our existing space, and the space that we're building to occupy in summer of 2012. We are at Hopkins University, the Department of Conservation and Preservation, the Sheridan Libraries, the director of whom, Conservation and Preservation, Sonia Jordan-Mowry, is our principal investigator, and our senior project conservator is William Minter. We conduct research that is particularly ambitious in scope and also designed to be particularly helpful to conservation and to conservators. So accordingly, the project that I'm heading up is looking at the role of metal cations in paper degradation, both hydrolytic and oxidative. Which cations are we looking at? Magnesium 2, because of its role in deacidification. We just did a review article on that. Aluminum 3, historically because of sizing, but many contemporary uses, I'll leave it with that. Iron 2 and copper 2 because of their roles in pigments and inks. The problems with the latter three are very well known to this audience. Corrosion, whether it's distributed throughout the sheet or localized to the application of the metal. Our innovations of approach, we work from the simplest systems before graduating to the more complex. So we draw very heavily on physical organic chemistry, then going to studying paper fibers in bulk water that's somewhat easy to study, relatively easy to study, and then I will present data on finished actual paper. Holding the ionic strength constant. Groups and individuals have been very concerned about this in the past. We're bringing the techniques and the arguments on board. Common ion effect buffers to control pH. In our samples, we control pH the way you calibrate a pH electrode using common ion effect buffers. Similarly, we control relative humidity for our samples the way you calibrate a hygrometer using saturated salts. And we age in inert gases as needed to separate oxidative from hydrolytic pathways of degradation. So some results of the simpler system of bulk water. We see degradation by aluminum compared to our kinetic ionic strength effect control, lanthanum 3, all those being equal. pH being equal, the sulfate counterion being equal, the ionic strength being equal. Magnesium 2 used for deacidification, no significant difference there. Nothing funny also going on between aluminum and magnesium together, boding well for deacidification using magnesium 2. As we increase pH, that slows the aluminum catalyzed mechanism down significantly, although there's some indication that the aluminum path may still be efficient. Now, actual paper. The results of one of our first two buffering systems for actual paper, phosphates. We see that on arrival, certain metals will depress the pH, but that in each case, the finishing and starting pH are the same. So that's not a problem for the buffering system. It means that we have to be very careful with our formulation of buffers only. And some results for that. We see substantial degradation of iron 2 and aluminum 3, but we have still two variables to control. The aluminum 3 is more acidic, the iron 2, not absolutely certain that we're controlling for the one-electron chemistry, the Fenton type mechanisms with which you're familiar. Conclusions in the future work. Working from simple systems to more complex, that's been a great success. That's the only way we can make any mechanistic arguments in paper degradation. Holding the ionic strength constant, check. Common ion effect buffers to control pH. That's been a great success as well. We've done phosphates, we've done acetates, we're working on succinates, bringing that buffering system on board. Saturated salt solutions to control RH check. Aging in inert gas is needed. As I said, we're still having some difficulties in controlling the one electron, the Fenton type processes, the way we're doing it. We have to do everything now in inert gas to stop that, so that's in development. Implications to conservation. One sentence on this. We need to really know the chemistry of these mechanisms of degradation to say, is a balanced iron gall ink safe? You can balance iron gall ink. Is it safe in the collections? Aluminum 3, when you increase the pH, the aluminum catalyzed pathway, when you increase the pH, it slows the mechanism. But are all deacidification modes safe? Which ones aren't? Finally, we have to look at chemistry very carefully to know the efficacy of accelerated aging. With that, I conclude. Thank you very much for your time.